Fractions. Probably the two most intimidating math words that people hear are calculus and fractions. People can get intimidated by calculus because they know it's math and they know it comes after all this algebra, but they've never really done it. Right? Calculus isn't really that hard, but it seems hard because we're not really familiar with it and it's advanced. Right? Fractions, on the other hand, people are scared of not because it's unknown, but because it's completely misunderstood. Fractions can be understood. They are logical. They make sense, but you have to be shown that logic. So let's get started. Let's look at a problem here. Let's pick my color. Let's say 6 plus 2. Does that have anything to do with fractions? Oh, not yet. If I make a number line here, I'll put my 1, 2, 3, 4, 5, 6. Plus 2, I'm going to go 2 more and get to 8. Continue to move in an indicated direction. If instead of going right, I want to go to the left, we know how to do that now. I actually have two options. I can continue to use addition, where that 2 goes to the left instead of the right, or I can use this new operation, subtraction, using the number that I'm used to. Now, let me make that a little more explicit. When we first start moving backwards, counting down, we don't introduce negative numbers. We introduce a new operation called subtraction. That means move the other way. So the other way from positive is negative, so I'm moving backwards. That gets me to 4 here. Right, 6 plus negative 2, 6 plus negative 2 is the same as 6 minus 2. Right? I have a new kind of number here that lets me use the original operation. That's exactly what's going on with fractions. Let me make a smaller ink here. 6 times 2, I'm taking my 6 and I'm not moving some other amount. I'm taking that 6 and I'm making it twice as long. I measure this out, duplicate it, and that gets me double 6, that's 12, right? 6 plus 2 was 8. 6 times 2 is different. That 6 times 2 is 12. Now, what if instead of making something move to the right, I want to make it move to the left? I can either put in a new operation to say move left, or use the original operation and introduce a new kind of number that's a left-moving number. Well, the same situation is going on with multiplication. If instead of making something twice as big, if I want to make it smaller, come on, 6 divided by 2, I take that 6 and I make it half as big. I take that big arrow, instead of making a single arrow that's double the size, take that single arrow, make a single arrow that's half the size. And that gets me to 3. So here's my new operation. Instead of multiplication, I have a new operation, whether I use this symbol called an obelus, or I use a slash. That also means division. Division's just making smaller instead of making bigger. This is starting to look like a fraction, and there's a good reason for that. There are two reasons why we don't just keep using the division sign over and over again, historically. One of them has to do with more complicated expressions, right? We talked about with subtraction, once we have more than two inputs, it's really convenient to be able to shuffle terms around, right? So we need to think of everything as addition, so you can use that associative property, keep the negative sign with the right terms here. So the same thing is going to be true with division. If I have a bunch of numbers all together, I don't know why it keeps making slashes there. 6 and 2 and 5 and 8 and 13. If some of these are slashes and some of them are multiplication, it's a little bit confusing as to what's making it bigger, what's making it smaller. Okay, so I've made it half the size, then 5 times bigger, then 8 times bigger, then a 13th smaller. Or what if I have 2 slashes in a row? Is 2 becoming 3 times smaller? No, it's just like minus here. It applies to what comes after it. So that's 6 cut in half and then cut into thirds. It's kind of hard to see what's going on there, especially when it's mixed up, especially when we also have addition thrown in there, when we have variables, we have parentheses. So it's a little bit smoother if I make that numerator and denominator very clearly separate. Right? That's what enables us to have expressions like this. We'll get into that more in intermediate algebra. But expressions like this, we can see what's going on much more clearly than if I have to write parentheses, divide by this times this divided by this. It's a little hard to see what's going on. Just like when we're simplifying expressions, some of you may do things like this, and you simplify it going across. Now that works, but it's a lot easier to see. Okay, here's 10. 10 plus 5 is 15. Okay, negative 2 and negative 3, negative 5 plus 15. 15 minus 5, that's 10, right? By having a new line for each expression, it's clear to see what's going on. And when we're typing in our answers into a text box on the computer, we don't have the luxury of this. Right? That's why most of the time on the computer, you're just typing in your final answer, but on your paper, you're organizing it in this way. So most of the time, I'm not going to ask you to type in all of these steps just because it's hard to see like that. Maybe you can hit a return and go here, depending on the text box that you're using. So in the email or in a Canvas message or something like that, even a text message, yeah, go ahead and hit return so you can have 4 lines here instead of just going across. But now we're getting a little bit sidetracked here, talking about fractions. By separating parentheses without using parentheses, by grouping the 3 and the x and the plus 2 all together as a denominator here, this is visually easier to see what's dilating. 6 plus x is going to make it bigger, assuming x is positive. Well, even if it's positive. Anyways, that's going to make things larger, more than 6 times bigger. and then this is going to make things smaller. Right? The other reason we care about uh, how we write our division is because there's a difference in how we understand numbers like this versus this. And there's some historical situations going on here. In this problem, what we see is two discrete numbers. I have 2, I'm cutting it into 3 pieces. This also means 2 cut into 3 pieces, or made 3 times smaller, skinnier. But we also, today, think about this as a number all by itself. It didn't always used to be that way. If I saw, let's see if I can make my circle here. If I have a circle and I then filled in this much of it, no, it didn't work out quite so well. All right, that's what I get for being fancy. I filled in this much of it. The way they originally first started thinking about fractions, and sometimes we still do this today, say if we're baking or something, is look at the smallest piece we can get. How much of the circle is that? That's 1/2. But then there's a little bit left here. How much is that? We'll find out eventually, but that's a 1/6. And they would call this amount 1/2 plus 1/6. These unit fractions are all that existed for hundreds of years, if not thousands of years. My history is a little rough, and all my books are locked in my office under quarantine, so I can't go do the easy research without having to just scour the whole internet. So 1/2 plus 1/6 is what they would call this shape, even though we would call it 2/3. Right? You take our circle, fill it in, 1/3, 2/3. What we call 2/3, they wouldn't have a concept for something like 2/3. It would only be halves and sixths. And so they wouldn't write it as 1/2 and 1/6. They just wrote it as that line over the top served to show that it wasn't twice as big, it was half as big. It was a half part and a sixth part. Just like they replace 2 with a 2 with a dash in front of it to mean go left instead of go right, they replaced 2 with a 2 with a line over it to mean 2 times smaller instead of 2 times bigger. Now, once we start thinking of these as units, so we can say 3/6 instead of saying 3/6 like that, we can actually show that as multiplication. 3/6. Or as we like to say, 3/6. Or even more compact, 3/6. Right? A fraction consists of getting 3 times bigger and 6 times smaller in this with these particular numbers, or 2 times bigger and 3 times smaller. That is the crux of what a fraction is. When I see A over B, over is not an operation. There's no, please excuse my dear over Aunt Sally, right? It doesn't fit in there. It's not anything. It's just a way to describe what's written here. You don't say dash 2, you say the opposite of 2, negative 1 times 2. We don't say over B. We either say 3/6 this many of this unit, or we say 3 divided by 6. They're all talking about the same thing.